Bismillahirrahmanirrahim. Now we will discuss pendant and methylols. Now we'll discuss pendant and methylols. The N-methylols react to release formaldehyde. See cellulose crosslinks. Cellulose crosslinks in the presence of an acidic solution will form cellulose and an intermediate product which will ultimately release formaldehyde. Fabric pH and formaldehyde release. Fabric pH has a great influence on the Mason jar test result. A pH of 7 will result in the lowest release values. However, if the pH is alkaline or acidic, all else being equal, the test will show much higher values. If the same swatch is resubjected to the jar test, additional formaldehyde will be released and test values will be in the same ballpark as the first run. The swatch will continue to give a positive release and values until all the crosslinks have been broken. The shape of this curve is explained by an understanding of the three linkages that are responsible for the formaldehyde release. Now we will discuss effect of pH on formaldehyde release. This graph shows the effect of pH on formaldehyde release. It is shown that when the formaldehyde is in basic solution, it will be released more, and when it is neutral, formaldehyde will be released possibly low, and when the solution is basic, it will be released more. The cellulose hemicetals are the ones that most easily revert back to formaldehyde monomer. They are the ones that are released at neutral pH. The pendant and methylols are unstable at alkaline pH. Fabric tested under alkaline pH would liberate both the hemicetals and the pendant and methylols under acidic Under acidic conditions, crosslinks are broken, so all the three linkages would contribute to the total amount emitted. Now we will discuss soil release finishes. Soil release is a term used to describe the cleanability of fabrics by the laundering process. The preceding chapter, from a consumer point of view, a stain is perceived to be the worst case of soiling. With use, fabrics tend to develop an overall gray and dingy look, and this too is undesirable. But unless the consumer has the original fabric to compare with, the loss of whiteness is not objectionable unless it is severely discolored. A visual stain, on the other hand, even a mild one, is more objectionable. First, we will discuss types of soil. Soils can be defined as unwanted substances at the wrong place. Most common soils fall into one of four categories. First, waterborne stains. Second, oil-borne stains. Third, dry particulate soils. And fourth, composite soils involving oil and grease absorbed on the particulate matter. Waterborne stains are not much of a problem. The stains are soluble in the wash water. Food stains and dried blood, although not water soluble, are respective to proteolytic enzymes found in the most commercial detergents. Dry particulate soils such as flour, clay, and carbon black are mechanically entrapped in the yarn interstices and reside on the surface of the fiber. Removal of particulate soil depends on overcoming the work of adhesion between the particle and the fiber surface, facilitating the transport of detergent solution to where they reside and transporting the particle into the wash water. Mechanical energy is important for later. Oily soils, for example, salad oil, motor oil, food grease, is particularly difficult to remove for synthetic fabrics such as polyester. The sorption forces between the oils and the synthetic fiber surfaces are so strong that it is virtually impossible to remove them by conventional laundering. For this reason, oil soils as a group are particularly difficult to remove from many washable fabrics made from 100% polyester and polyester blends. Lipstick, makeup, printing, ink, used motor oil, and atmospheric soot are examples of composite soils where bonding to the fiber is a function of the oily component. The removal of these stains is accomplished by overcoming the sorptive forces. Now we will discuss how fabrics are soiled. Soil can be airborne particles that settled by gravitational forces or are electrostatically attracted to the fabric. Soot is a troublesome airborne particulate that is difficult to remove from fabrics. Drapes, carpets, and upholstery are items prone to being soiled by airborne soils. Soils can be transferred by contact with a dirty surface, and then they can be ground in by pressure or rubbing. Soils can also transfer by wicking. Liquid soils in contact with fabrics will wick into the structure by capillary action. Soils removed in the Laundering process may redeposit it back into the fabric. Emulsified oily soils may break out of solution unless the emulsion is well stabilized. Also, the ionic charge of the emulsified soil may be attracted to an opposite charge on the fiber. Now we will discuss the soil removal process. First of all, particulate soil. The adhesion between particulate soil and the fiber depends on the location within the fabric structure. The forces of attraction between the soil and the fiber and the area of contact. Studies have shown that as more energy is used to grind particulate soil into the fabric, the more difficult will it be to remove them. Both the area of contact and the location within the fabric are influenced by the force. Removal of particulate soil is brought by breaking the adhesive bond between the particle and the fiber, wetting out the particle to make a stable dispersion, and then carry out the dispersed particle into the bulk of the wash water. The greater the area of contact, the more difficult it is to break the adhesive bond. Fine particles have a greater area of contact. The tighter the fabric, the smaller are the interfiber voids, which make also the outward transport more difficult. Now we will discuss the removal of soil from oily soils. The basic interaction between a liquid and solid was discussed in this previous article. It was shown that the thermodynamic work of adhesion is given by the Young-Dupree equation. This is the Young-Dupree equation. From this, it follows that those liquids that spread on a surface will have a zero contact angle. Since the cosine of 0 is 1, the work requires to remove that liquid will 2 times the surface tension of the liquid. Most oils have a surface tension of about 30 times per centimeter, so they will completely spread on nearly all fibers except Teflon. First of all, we will discuss roll-up mechanism. Oily soil removal will depend on three-phase boundary interaction that occurs in the detergent solution. The roll-up mechanism first postulated by Adams argues that for removal to take place, the surface forces generated at the three-phase boundary of fiber detergent solution oily soil results in the progressive retraction of the oil along the fiber surface until it assumes a contact angle of 180 degrees. Here, the work of adhesion is zero and displacement is complete. This figure shows the rolling up process of a soil release. There are total 7 phases of rolling up process. In the first phase, the soil particle is straight, but in the last phase, it develops the shape of a bubble. Second, we will discuss roll-up thermodynamics. The surface forces responsible for three-phase boundary between fiber detergent and oil can be represented as interfacial tension vectors. The forces responsible for roll-up is the resultant of interfacial tensions as expressed by the equation. R is equal to gamma F by O minus gamma F by D plus gamma O by D multiplied by cos theta D, where gamma F by O is the interfacial tension between fiber and oil. Gamma F by D is the interfacial tension between fiber and detergent. Gamma of O by D is the interfacial tension between oil and detergent. And theta is the dynamic contact angle. This figure shows the fiber-oil interaction. It shows that oil and fiber interact at which angles. In order for the dynamic contact angle to change from 0 to 180 degrees, the resultant must be positive. R is positive when the quantity is greater than the oil detergent interfacial tension. It follows that when R is greater than 0, the contact angle increases. These figures show the contact angle these figures show different contact angles of oil and detergent. On the other hand, when R equals 0, the contact angle is in equilibrium and the oil stops receding. However, if R is less than 0, the contact angle is smaller and the drop spreads on the surface. From this, it follows that roll-up spontaneous release occurs when interfacial tension between fiber and oil minus interfacial tension between a fiber and detergent is much greater than interfacial tension between oil and detergent. And that redeposition occurs when interfacial tension between a fiber and oil minus interfacial tension between fiber and detergent is much lesser than interfacial tension between fiber between oil and detergent. It is well to remember that 1-0 interfacial energy exists when the attractive forces operating between molecules of a liquid exactly equal the attractive forces operating between the outermost molecules of a solid. Cotton or other hydrophilic fibers will have very low interfacial tensions with water because of hydrogen bonding. Second, high interfacial energy exists when Second, high interfacial energy exists when one surface is non-polar and the other is polar. For example, hydrocarbon oils in contact with hydroxyl or ionic charged solid surfaces. It is known that cellulosic fibers have good oily solid release. On the other hand, polyester fibers are known to have poor solid release. It follows that therefore that for spontaneous soil release to occur, the fiber surface must be hydrophilic and the balance of interfacial energies must be according to this formula. Interfacial tension between oil and fabric must be greater than interfacial tension between oil and detergent. From thermodynamic considerations, non-polar finishes such as silicones, polyethylene, and fluorochemicals release the interfacial tension between the detergent bath and the fiber and therefore should make soil release worse. The data support these thermodynamic predictions since both the fluorochemical and the silicone finish on 100% cotton fabric reduce the amount of soil removed. Now we'll discuss the effect of hydrophobic surfaces on soil release. When the soil release is when unfinished cellulose is treated, 95% soil removed. When the acrylic latex finish method is used, 88% soil is removed. When fluorochemical method is used, 60% soil is removed. And when silicones are used, 45% soil is removed. Soil was a mixture of iron oxide suspended in oleic acid. The detergent contained an anionic surfactant. Fabric was 100% cotton. Now we'll discuss soil release chemicals. The introduction of polyester cotton blends in the early 1960s brought to light the need for soil release chemicals. Up until that era, most all washable fabrics were constructed of 100% cotton. The laundry processes included high wash temperatures, harsh chemicals, and starch. Harsh chemicals include caustic chemicals, dye, and bleach. Most all normal stains could be removed from these fabrics when polyester entered the picture. Oily stains become more difficult to remove. About the same time, the home laundry procedures were changing. Lower wash temperatures and less harsh chemicals evolved to prolong the life of durable press finishes. Also, starching became unnecessary as the garment did not require ironing. Millikan can be credited for being first to introduce the soil release durable press finishes to press fabrics to the consumer. They incorporated an acrylic acid copolymer into their electron beam curable DP finish and merchandise the fabric under the visa label. Shortly thereafter, the result of the industry followed suit with a host of different soil release finishes. In general, soil release finishes are film forming polymers capable of imbibing water. Today, the number has stabilized into three distinct varieties. Two types work well on a durable press finish cotton polyester blends, for example, acrylics and dual action fluorochemicals. These are added into the final DP finishes. A finished bath. A third type is engineered specifically for 100% polyester fabric, for example, exhaustible. They are best applied in the dye cycle, although they may be applied by pat dry cure. Now we will discuss acrylic soil release finish. The chemical composition Now we will discuss acrylic soil release finishes. The chemical composition of the acrylic acid finishes may be generalized as follow. This is a structure of acrylic soil release finish, where X is hydrogen or methacrylic, R is methyl or ethyl, and A is 30 to 100%, and B is 70 to 30%. Now we will discuss polymethacrylic acid, PMAA. Polymethacrylic acid is completely water soluble and functions as a soil release finish. However, the proper amount of cross-linking is necessary before the finish to function properly. Table below shows the soil release rating is influenced by the inclusion of diepioxide. When PMAA is cross-linked with the only diepioxide, marginal SR ratings are obtained. However, if a small amount of diepioxide is added with DMDHEU, the soil release ratings are very vastly improved. Increasingly, the amount of diepioxide causes the SR rating to drop again. This data supports the contention that the ultimate properties of the cured film deposited on the surface of the fiber determines soil release. This is the table which shows the effect of cross-linking. When a PMAA is added with 14% diopioxide, the SI rating is 2. When PMAA is added with 21% diopioxide, the SI rating is 2.5. When PMAA is added with DMDHEU and 1.2% diopioxide, SI rating increases to 4.5. But when PMAA is added with DMDHEU and 3% diopioxide, the acid rating drops to 2.5%. Now we will discuss methacrylic acid, ethyl acrylate copolymers. Monomers containing carboxylic acid groups can be polymerized with vinyl or acrylic monomers to yield a range of copolymers varying carboxyl content. Copolymers of methacrylic or acrylic acid and ethyl acrylate have been found to be particularly useful as soil release agents. An acid content of 70% or less give a relatively high molecular weight emulsion, whereas polymers, whereas higher proportions of acid render the polymer water soluble and of lower molecular weight. A particularly good combination for soil release is 70% methacrylic acid and 30% ethyl acrylate. The data shows that when 70 to 30 copolymers added to a typical durable press finish containing DMDHU, the fabric possesses excellent soil release with fair durability. This data also shows that SR ratings are substantially lowered if diopioxide over cross-links the polymer.